Good morning, everybody. Welcome to the first session on distribution and networking. We have 5 super interesting papers, of course, and Fengyun Liu will open the session with work on initializing global objects. Floor is yours.
Hello, everyone. Glad to meet you here at OOPSLA. I'm Fengyun from Oracle Labs. I'm going to talk about our work on initializing global objects. This is a joint work with Lhoták, David Hua, David is here, and Enze from University of Waterloo. Programming languages have made great progress on many aspects over the years. However, there is one aspect that hasn't changed much since the beginning of computer programming, that is global variables. Global variables exist in almost all languages, from Fortran to the Litany, Rust, and WebAssembly. Global variables is a controversial language feature. It's well known that global variables, they cause all sorts of problems. They usually have subtle initialization semantics. Their initialization is unsafe. They break modularity. They are prone to data races. They make testing of programs more difficult, and so on. However, mainstream programming languages, they do not offer any help in improving the situation. It is a big mess. The question is, as programming language researchers, can we do better? Our work shows that it is possible to make the initialization of global variables more principled. Global variables exist in object-oriented languages in 2 forms: static fields, as in Java, and global objects, as in Scala. We base our work on global objects. As we will say, the essential complexity is the same. The problem of initialization safety can be illustrated by this simple piece of code. So here we have 2 objects, A and B. In the object A, it contains a field A, which is initialized with the field B, and vice versa. It is obvious that this piece of code is problematic. To the least, at runtime, the code will read, I initialize the field, which is always an error. Even worse, in the presence of concurrency, if the 2 objects they are initialized from 2 threads concurrently, then this piece of code can lead to deadlocks. This is because in the setting of multi-threads, to initialize a global object, we have to first grab a knock on the object so that we can avoid initializing the object twice. Now suppose one thread grabs the knock on A, and the other thread grabs the knock on B, then they will wait for each other forever, a good recipe for deadlocks. We approach the problem with flow-sensitive interprocedural analysis. This way, we can relatively easily avoid reading uninitialized fields. We exclude type systems from the solution space in the beginning due to its verbosity in spite of its many advantages. The usage of static analysis raises the concern about its modularity, performance, and the explainability of error messages. We will eventually address these concerns. To deal with deadlocks, a natural idea is to require that the initialization of global objects, they form a partial order. We can use the static analysis to construct an initialization dependence graph. For example, here, it's easy for the static analysis to figure out that the object A, its initialization depends on object B and C, and B and C depends on object D. Now, if the initialization dependence graph is acyclic, we can be sure that at the runtime, there will be no deadlocks in initializing global objects. It seems that at this point, we have solved both problem of initialization safety related to global objects. Are we done? Not really. So if we set out to enforce partial ordering using static analysis, we would soon run into a problem which we call the curse of modularity. Basically, the problem is that we cannot correctly construct the initialization dependence graph without doing whole program analysis. We illustrate this point with this piece of code. So here we have three objects, object A, B, and C. In the object A, it has a mutable field f, is initialized with this function, which just returns the string hello. In the object B, it contains a field B, is initialized by calling this function f. And finally, in the object C, there is a field C, which is initialized by appending word to the field B. We might expect that the initialization dependence graph look like this. And at the runtime, we might think that the field C holds the value hello world. But that's not necessarily true. Look at this slide. The only change we did is to mutate the field f of object A at the beginning of the program. So instead of returning just the hello, it read the field C of object C. Now, suddenly, the object B, its initialization would depend on object C. So now we have a cycle in the initialization dependence graph. And at the runtime, the field C, it has a value null world, because when we read this field C in the function f here, is not yet initialized. The lesson of this example is that to correctly construct the initialization dependence graph, we have to do whole program analysis. This is where we are. We wanted to use static analysis to ensure initialization safety, but we found out that we cannot avoid whole program analysis. This is bad news, because both for performance of the analysis and for explainability of error messages, we want to avoid the whole program analysis. Facing this difficulty, we take a bold step in proposing a design principle which we call initialization-time irrelevance. Roughly speaking, the principle says the state of a global object at the end of its initialization should not depend on when the object is initialized. We argue that this is a good design principle. First, it enables modular reasoning about initialization. No whole program reasoning is needed. Second, it avoids semantic surprise to programmers. Programmers in daily program, they rarely care about when a global object is initialized. It implies that initialization time should not make a semantic difference. Otherwise, it will be a surprise to programmers. Initialization time irrelevance avoids such semantic surprises to programmers. And third, because the objects they can initialize at any time without semantic difference, it enables the compiler to perform more optimizations. And finally, as we will see, initialization time irrelevance, it allows flexible initialization patterns, which is sufficiently expressive for practical usage. Now we have the principle. The next question is how to enforce the principle. It turns out that to enforce initialization time irrelevance, it suffices to follow this rule. The rule says, during the initialization of a global object, it is forbidden to read or write the mutable state owned by another global object. A mutable state is owned by a global object if it is allocated during the initialization of that global object. So this rule suggests that we have to track ownership of mutable state in the static analysis. We illustrate this rule using this example. So here, as we can see, we define a class box which contains mutable state. In the object A, During its initialization, we create an instance of box. Therefore, this mutable state is owned by the object A. Similarly, in object B, during its initialization, we create another box. Therefore, it's owned by object B. At the next line, we can alias the box A created in object A to another field of object B. That's OK. Aliasing does not change ownership. The next line, if we try to read the mutable state of box B, that's OK because the mutable state is owned by object B. The next line, if we try to read the mutable state of box A, that would be an error because the mutable state is owned by object A. It violates initialization time irrelevance because the mutable state here could have been changed by the main program. Initialization time irrelevance doesn't require heap separation by owners. It's perfectly defined to mix objects of different owners in the same data structure. Here is one example with we have the same box definition here, and in the object A, during its initialization, we create a mutable box which is owned by object A, and in the object B, we create an array, a mutable array. So we can put the alias of box in this mutable array. So as you can see from this heap graph, the boxes is owned by the object B, and the box is owned by object A, and then we have a pointer from boxes to box. That's perfectly fine. And at this line, if we read the alias stored in the mutable array, that's OK, because boxes, the mutable state is owned by object B. At the last line, however, if we try to read the mutable state in the box, it will be an error because box is owned by object A. It violates initialization time irrelevance. The combination of partial ordering and initialization time irrelevance enables us to statically schedule the initialization of global objects. For example, here, the static analysis can figure out that the initialization of object B depends on A. Using this knowledge, the compiler can initialize the objects at the beginning of the program according to the topological ordering. This way, it can remove all the runtime checks about whether a global object is initialized or not. Alternatively, it may also initialize the objects at build time, as it is done in native image and ahead of time compiler for Java in the GraalVM project. This way, the compiler can perform more partial evaluation optimizations. So this is where we are. With the help of initialization time irrelevance, we managed to avoid whole program analysis. The modularity makes the analysis fast, and also the error messages, they are easier to explain. However, this solution is still not ideal. It suffers from a usability problem related to context sensitivity. We do not have time to talk about it here. So the only thing I'd like to mention is that in the paper, we introduce region context to make the analysis, in particular context sensitivity, more explainable and tunable, so that it can support complex use initialization patterns. The final solution is still not perfect in terms of modularity, in the sense that the checker would, it may analyze code across project boundaries, but nevertheless, we think that's the best solution we can achieve at the moment. Our analysis is integrated in the Scala 3 compiler. So as you can see here, if we feed this piece of code to the Scala 3 compiler, and then we will get a warning like this. As you can see, the warning reports a violation of the initialization time irrelevance. In addition to that, it shows a call trace from the root of the global object to the place where the violation happens to facilitate debugging of their problem. So that brings us to the end of the talk. Thanks for your attention. If you have questions, I'm happy to answer.
So if you have questions, please use the mic and the next speaker.
Hi, thanks for the talk. How does your system, can you go back to the example you just showed? How does your system know that boxes 0 is a box that is an alias for the data inside the array?
Okay, so the analysis tracks all the information.
But I mean, so in Rust, for instance, right, you have lifetime parameters, and you can sort of specify in the type signature that vector get, the lifetime of the input vector is related to the lifetime of the output reference, and that's how you know there's an aliasing relationship, and that's user configurable. And I'm wondering if this is baked into your analysis, or if I come in with a new Scala data structure, like a hash map or other things that I want to track alias relationships. Is that something I can express in user space? Or is that something that I would have to modify the analysis in order to understand which methods coming out of my hash map produce aliases for data in the hash map?
So currently, with the analysis doesn't provide a way to specify ownership. By default, it assumes that if a mutability is created during the initialization of a global object, then that mutability is owned by the object. Mm-hmm. In terms of the precision of the analysis, it's possible that we introduce a region context. So the user, if they want more precision and to want more complex initialization patterns, it's possible to have more precise analysis for those to distinguish those objects. Yeah.
Okay. Thanks.
Just a very short question. How does your system interact with non-determinism in the constructors, such as depending on a global random value?
Oh, pardon?
So how does your system, your static analysis track non-determinism in the constructor of an object, like global random values that are not based on initialization order?
Yeah, good question. So we didn't mention in this talk. So non-determinism, and also if just the user in the constructor, if they call the random number generator, then it will validate this initialization-time irrelevance principle. So the way we do this, because we are using the static analysis, it means we are able to track all the effects during the initialization of a global object. So it can produce warnings for those unintended effects.
Thanks.
Okay, let's thank Fengyun again, also because this is a distinguished paper.